need to do with this?
That other one is scheduled.
That probably is optional.
Yeah, we shouldn't call anyone late.
Ethan, I have written extensive notes. Should I put them on Slack?
You should have access to a Google Drive folder for that. You can
Okay.
also put them on Slack.
In which channel?
There's a lectures channel, I think.
Lectures.
Yeah, just lectures.
And the students have access to it, obviously.
Yep.
Okay.
So not the one there's lecturers only, that only we can see, but there's one that's just for lectures where they ask questions.
They're kind of rough. I don't want them to be circulated. I didn't add references and this kind of thing. But
Okay, sure. Then yeah, Slack is private to just the students here, so that would be
yeah.
I'm sure they'll appreciate it.
Yeah. Yeah, we started early. That was a strategical error. That-
We were expecting it to run over.
I'm jet lagged, so for me it's like already like a half day. That's good. New York? It's like 2 hours.
They feel it more this way than the other way.
Yeah, I don't feel it actually. I was just joking. It's 2 hours. It's nothing.
Oh yeah, I heard of
My
Liam
minor
even
income.
talked about this ADS-CSS.
Who?
Liam Fitzpatrick. It's less than
8 years ago. There was a big, but
he was doing it for the O2 model.
yes. Well, that's why it's here. This is gonna be just an example, but
Yeah.
you can do it in many theories. This is the work with Ferduli, right? Yes.
Shall we go?
All right.
Okay.
All right, let's try starting again. We'll see if 20 more students walk through the door for the second time. All right, Zohar, everybody.
Okay, I'll just repeat what I said. The unifying theme of my 4 lectures will be how semi-classical physics field arises from large quantum numbers. So all these topics are going to be interconnected by that idea. So today I'll start with some motivations of why this is an interesting topic connected to very interesting emergent phenomena, many-body physics, and also to experiments. And then I'll do an example today in some detail. That example probably would not be familiar to many of you. That's the example of the effective field theory of cold gases. And then I'll go through some interesting example of conformal symmetry, just to explain that that's going to be this interaction is kind of slightly singular. At the origin, it's just quantum mechanics problem that you could have seen in undergrad, but it's very subtle. It has RG flow, fixed points, and many, many interesting phenomena that I'll explain. We'll go through the state operator correspondence, and then at the end, I'll do 2 concrete examples. I'll do one slightly model, trying to explain how semi-classical physics emerges, and I'll show you comparisons with simulations and some experiments. And finally, I'll finish with a general idea about many-body systems, which is that they're all asymptotically free small angles, which is called angular momentum. And then I'll show you that in this regime of small angles, even for non-holographic theories like the Ising model or the O2 model, you can take the CFT correspondence. So the idea CFT correspondence is something that we usually learn is extremely specialized for some theories with large N, maybe strong 't Hooft coupling, some theories that are very far from nature. But I'll show you that there is a piece of that dictionary that applies always, even in models that can be realized in the lab, and it was tested. So these are the topics that I'm going to cover. I also wrote very extensive notes. I'll try to put them on Slack tonight after fixing a few things. And those notes are a little rough. I didn't add references or credited many people that deserve to be credited, so please don't spread them around. It would be embarrassing. I need to fix the references, and then maybe I'll put them in a more public domain. Okay, so let's let's start. I'm gonna start with some motivations, and then the cold gases. So the motivation is pretty simple. We know that this is the famous adage from Anderson. Problems where you have many particles and sometimes also strong interactions, they lead to extremely interesting emergent phenomena. And I think it's very fair to say that this is the biggest open problem in physics, and it's the most important one, to understand how exactly you go from very simple microscopic Hamiltonians to interesting phenomena such as superfluidity, superconductivity, symmetry breaking, confinement, Hall states, and whatnot. The list goes on. So we're going to study an aspect of this. Of course, there are many approaches. There are people that do simulations. There are people that do perturbation theory, which often doesn't work. Today, we'll study an approach to this problem that has to do with taking some limits of large quantum numbers and trying to study strongly coupled many-body systems in some regime with large quantum numbers and seeing how the models become classical, almost classical, or semi-classical. So that will be the main point. And then we'll test it. I'll show you that this can be actually tested. So this is the big problem. So for instance, if you plot the energy spectrum of some complicated many-body system as a function of the total number of particles or the total charge, it's very heuristic. I'm not specifying a model yet. But typically, that you have some very complicated many-body system and you want to study fixed Q could be a U1 charge, for instance. So Q could be a U1 charge. So the vacuum, so this area of like small q, you might need to do numerics or experiments. It's going to be pretty much out of control. But then when the charge is very large, typically you might be able to find the new semi-classical description, and you might find some energy eigenstates or approximate energy eigenstates. And you might find some excitations, approximately, up to very small corrections. So you might have a lot of control when Q is large. And then, of course, you lose control typically, and you get some complicated that we almost have no hope of understanding analytically. This is the regime of maybe something like random matrix theory. Typical excited states are very complicated. So maybe here you might think that you need maybe random matrix theory or some probabilistic tools, but you can't really hope to find the eigenstates explicitly. While here, there might be some interesting effective field theory. And this is where there are interesting emergent phenomena. The effective field theory might have completely different degrees of freedom from the ones you've begun with. And another general thing about this kind of picture is that even if H bar is very large, effectively, by that I mean that it's strongly coupled, when you go to this regime with large Q, it's often the case that you find an effective H bar, which is given by the original H bar divided by some very large number. And the power here depends on the model. So you find some new emergent semi-classical physics. And the same diagram is true if you, let's say, fix the angular momentum. So I could draw the Q is replaced by J. We expect the same thing. And I'll just mention one special case now. That's the case that I'm going to analyze in most detail in these lectures. Well, typically, you don't really expect to find energy eigenstates with small energy when Q is large. When you lower the energy below some critical line, let's say. So this would be like the ground state at that fixed Q. And then this would be excitations above that. Okay? And so when we talk about emergent phenomena, we talk sometimes about this kind of, that there are some completely new degrees of freedom, and you'll see an example today. Any other questions? Okay, so I'm going to concentrate on when we talk about many-body problems, it's way too general. There are way too many examples and too many kinds of things to talk about. I'll talk about something that's closer to high-energy physics. So for me, except for today, where I'll talk about cold gases just to get your intuition ready for this kind of exercise. But the main goal really would be to talk about conformal field theories. So for me, except for the first lecture, many-body would be conformal field theory. Conformal field theory is, in a sense, the most strongly coupled system you can imagine. This is the most strongly coupled system you can imagine. This is because it doesn't have small parameters usually. So h bar is kind of 1. And in conformal field theory, we can ask, so famously, we cannot say almost anything about interacting conformal field theories without supersymmetry, etc. But we will discuss the following problem, and we will apply the tools of effective field theory to try to settle the following problem. So I'll review all of that, but I'm just giving you some motivation. Famously, in conformal field theory, there are local operators. These are the operators by which we can use to heat the vacuum or measure their correlators. These local operators have some scaling dimensions delta I. These scaling dimensions have played a very important role in the theory of phase transitions. The lowest scaling dimensions characterize the macroscopic properties of the system, the susceptibility, heat capacity, and so on. But abstractly, conformal field theories have a list of operators and the list of scaling dimensions. And we know very little about scaling dimensions in principle. So what I'll show you in these lectures is that, let's say, if we plot the scaling dimensions as a function of the angular momentum of the operators, let's say we want to understand, given an angular momentum, what are the operators with that given angular momentum? So you can solve it in free field theory, but for interacting conformal field theories, we know nearly nothing. So in this regime of small angular momentum and small scaling dimensions, I can't really say anything new in these lectures. Here there is plenty of other methods. So there is Monte Carlo. People simulate conformal field theories on the computer. There is Bootstrap, which is an algebraic approach to trying to determine those scaling dimensions. So there is Bootstrap, there is Monte Carlo, there is experiments. There is, of course, experiments, measure critical exponents that have been going on for at least 100 years. But the new thing that I'll teach you is that when you go further away in this diagram to large momentum, we will be able to understand a lot about this regime. So scaling dimensions which lie here, we will be able to understand. And I'll, just a second, I'll even argue that there is asymptotic freedom here. So I'll show you that there is asymptotic freedom in a sense. It's a new kind of asymptotic freedom, which allows to do exact calculations here. And in a sense, in this regime, the ADS-CFT correspondence is exact. So also exact, this is a regime where the ADS-CFT correspondence will hold exactly. Let me just raise the word. Okay, so that's one of the things we will see, that there is an effective field theory here. You can do exact calculations. You can compare to experiment, Bootstrap, Monte Carlo, and it's a very beautiful story, similar to that general philosophy. And we'll do the same with global charge Q. Yes?
So when you say small or large, what scales that you have in mind?
So let's say you take some abstract conformal field theory. What's your favorite one?
Could you repeat the question?
Okay, so the question is, what do I mean by small or large? So what's your favorite conformal field theory? Huh?
D1D5 CFT.
5D.
D1D5 CFT.
Oh, D. Okay, so the bad news The bad news is that I'm not going to talk about dimensional CFTs here. CFTs like 3D-izing, O2, 4-dimensional CFTs like n equals 4, Banks-Zaks. The two-dimensional story is actually far more complicated. The effective filter here is far more complicated, and I don't have enough time to explain it. That's bad news for you. But if you also like 3D CFTs, such as, I don't know, Ising 3D is a famous big problem, no? So large means much larger than 1. It's a matter of taste. Does asymptotic freedom, you can ask, when does asymptotic freedom hold? It holds when the distances are much smaller than inverse GeV. That's 10 to the minus 15 meters. Of course, it gets better and better the shorter the distances are. You can try to push it. Similarly here, it's going to work very well when J is 100. Is it going to work well when J is 3? It actually does, but it doesn't have to. Okay? So there will be some asymptotic freedom at small angles here. And I'll argue that any interacting CFT becomes actually weakly coupled at large angular momentum. And similarly at large charge. Yes?
So if I want to study O2 CFT, there should be another axis here. What part of, so it should be a
Q?
Yeah.
Yeah, I was.
What part of this diagram?
Right. And the question is, what about the axis of Q? So I'm not very good at drawing, but there is another Q here. So there is some, you should imagine some three-dimensional plot where for any given large J and Q, there will be some, we call it the ground state at fixed J and Q. And we will discuss it. There is a very interesting phase diagram as you scan that two-dimensional plane of what kind of things you might expect. They're completely different emergent phenomena in different domains of that parameter space. Okay? I'll get to it. Okay, yeah?
Can I ask about the comment of ADS CFT? This EFT will be weakly coupled.
Yes.
So usually in the ADS CFT, then the bulk is strongly coupled, right? So is there like a useful aspect of having?
Yeah, so the question is whether this ADS-CFT kind of correspondence is useful. So operators with large spin are hard to measure in the lab. But in the last 5 to 10 years, there's been concentrated effort on measuring them because of these many predictions. People made many, many predictions, and there was a lot of effort to measure. By now, a lot of numerical confirmation of what's going on in this regime, from simulations and from various other methods, Bootstrap, etc. ADS-CFT here is useful because it's like when you want to do computations in asymptotically free theories, there is a Python model, right? So that's how people actually do computations. They use a Python model. ADS-CFT turns out to be that. ADS-CFT is a Python model which allows you to close your eyes, think about particles doing something in ADS, and calculate systematically the properties of this regime. So ADS-CFT is like the Python model for asymptotic freedom.
But somehow the ADS, the pulse here, it will be strongly coupled.
No, it will be a Python model. You'll see. This will be in the last lecture. Okay, before that, I'll do various other things to prepare. And also, if you want to read before, I'll just put everything on Slack today, and you'll see.
Small clarification, when you said Python model, are we thinking of QCD?
It's going to be the Python model in QCD is for short distances. Here, I'm going to argue that at small angles, there is a Python model. It's a different kind of thing. It's a Python model that appears at small angles, and it's very easy to describe within the ADS-CFT correspondence. And it gives exact predictions for 3D Ising or O2 model or n equals 4. Okay. Okay, so this is the motivation. But to get there, I want to teach you how semi-classical limits even arise at large quantum numbers. So I'm going to start with a problem from called atoms, or atomic and molecular physics. It's rarely studied in HepTH, but maybe, oh, let me just, I think it's interesting. It's very interesting, and it's the subject of the 2001 Nobel Prize in Physics. So I'm going to start this topic now, called dilute gases. Actually, I think one of the Nobel Prizes went to Colorado, right? Yes. So there were 3 groups that did that at the 2 groups. Okay. Wyman is the name?
And Cornell.
Yeah, good. So that's a very, so maybe the students from Colorado already know all of that. So so I'm going to explain the problem. It's an under problem where you try to solve a Schrodinger equation of many, many particles, but you can't. At some point, you have to put it on the computer. You run out of steam. You can solve the 2-body problem at your dorms later, but at some point, you'll run out of steam. People have done extensive numerical simulations of this Schrodinger problem. And I'm going to show you how to solve the problem with semi-classical techniques. You don't need to do any simulations. You can just solve the problem by a smart approximation. So the problem is that we have some kind of confining potential. It could be a bucket. It could be some harmonic potential. That's what they did in the experiments originally. So we have some confining potential, which I'll call VTR. TR stands for trap. So trap. And it's going to be a function of the distance from the origin. It's going to be axisymmetric, so only a function of the distance, not of the direction. So I can just put absolute value here. And then what we're going to do is that we're going to place n particles here, bosons. I'm going to place n bosons in this trap. And and of course, if we only had the trap potential and no boson-boson interactions, then the wave function is just a product of the single particle wave functions in the trap. If the trap is quadratic, you can solve it immediately. There is nothing interesting. But the point is that there will be some short-range repulsion. So you have to come up with a model for repulsion. So another ingredient in this problem would be some short-range repulsion, which I'll denote by short range. And it's going to be a function of the distance between the particles only. Okay, so it's going to be 2-body, only 2-body. That's why the gas has to be dilute. I want to consider cases where 3 particles collide. We'll just assume that it's dilute enough that 3 particle collisions are negligible. So there will be some short-range repulsion. 2 particles approach each other, and you have to come up with a certain model for what is this short-range potential. And so one thing you could do is you could just choose this potential to be, let's say, a hardcore potential, where if the distance is smaller than some number, it's going to be infinite, and otherwise it's 0. That's the simplest minded thing you can imagine. And so the Hamiltonian is just a non-relativistic Schrodinger problem. I'm just going to write it for the sake of completeness. So this is the kinetic energy from each particle. And then we have the potential energy because of the trap. Okay, so this is, and then we have the 2-body repulsion. Okay, so this is the Schrodinger problem, and you can try to solve it for 2 particles, 3 particles in the trap. So the number of particles is just the range of, so I goes from 1 to n, and here I smaller than j. Okay, now you don't really want to commit too much to this particular choice of short-range potential. What if the actual potential between the atoms is not that? It's something slightly different. So the point is that in the dilute gas approximation, we will justify a little bit posteriori. All that matters is the S-wave scattering. So for instance, if you remember your scattering theory basics, for this potential, there is some phase shift when you scatter at any angular momentum. So in this model, delta L goes like the momentum times A to the power 2L plus 1. That's the phase shift in this. And a very common approximation is to assume low enough energies so we can neglect the L wave scattering and P wave scattering and just concentrate on S wave scattering. So that's just delta 0. That's the most leading thing at very low temperatures when you're close to the ground state and the momenta are very low. So the question is, what exactly do we put in the short range potential to really mimic that idea, that there is some degree of universality and we don't care about L wave scattering? So first of all, so there is the idea of universality that it really doesn't matter what you're going to put here. But if you want to be rigorous and put on the computer a potential that is exactly only S wave scattering, you can read about something that's called the Fermi pseudo potential. That's something from the 30s of the last century. It's an invention for a particular formula for the potential, which really just focuses on the S wave scattering. So it's like the shortest range. It's like the shortest range potential you can imagine. Okay, I'm not gonna delve too much into it because it really doesn't matter what the potential is. But there is a formula for a potential that only has the shortest range, just S wave. Is that clear? Or are there any questions about it? So that's the model that you want to solve when the number of particles is very large. And I'll show you how to go about it.
When you say S-wave, is that the same thing as acoustic scattering?
S-wave, I mean just, so you see in this formula, this tells you more or less how strong the scattering is if the two particles are heading towards each other directly versus if they're heading towards each other with some rotation.
Oh, I see.
So you see that here, heading towards each other with some rotation, that corresponds to L equals 1 or L equals 2, etc. And it's very small at small k, so at low energies, because of the centrifugal barrier, essentially. So when the particles collide with some angular momentum, they can't really touch each other because of the centrifugal barrier. And the or the scattering phase shift is very, very small. But still, it's there, and it's annoying. So people always want to put in a potential that says that if they're heading towards each other with some rotation, there is just no phase shift. They just go through. There is no scattering whatsoever. So an interesting model for a short-range interaction is one where there is anything happening at all, only if they're heading towards each other head-on, with no relative angular momentum. So if they have some impact parameter, there is nothing. Only when they're heading head-on. Okay? So it's difficult to write a potential that does that exactly mathematically, but Fermi has a formula. You can read about it later. It's not going to be super important for these lectures. Any other questions? Okay, so the question is, how do we approach the large N limit? How can we hope to find the ground state and the energy eigenstate? Well, the energy eigenstates in the large N limit, right? That's the question here. You can, of course, put it on the computer, as I said, but we'll try to do it more analytically. So first of all, I'm going to recast this question in second quantization. It's completely equivalent. I mean, it's just more streamlined, where you can discuss the number of particles in. You don't have to put it in the sum. It's going to be more streamlined. So we're going to write an action. Let me just show you. This is just the second quantized formalism of ordinary Schrodinger quantum mechanics. So we have a first order derivative kinetic term. That's because the Schrodinger equation is first order in time. Then we have the kinetic energy. There is no I anymore. So this is like a second quantized wave function. Then we have the trap. And finally, there is a short range interaction, which is repulsive, and it's called G. And it's a quartic term in the action. So this is an action for a field psi, which is a function of x and t, but it's first order in derivatives, so it's just equivalent to the Schrodinger equation. And the number of particles is hidden. We don't have an explicit n, except in the normalization of this wave function. So if you integrate the wave function over space, that should be exactly n. And that tells you how many particles are there. Yes?
So, well, you only have signals, will have chosen your exact potential to be like a delta function or something?
So that's exactly what I'm going to get into. How do we go from the short range potential here to this quartic interaction? I'm going to explain that now, exactly now. Yeah. Any other questions? So what's the connection between the second quantized formalism and the first quantized formalism? In this field theory, there is a tree where psi goes to e to the I alpha psi. And the charge under that U1 symmetry is the number of particles. That's what's written here. This is the J0. That's the charge density, or the particle density. You integrate it, and you get the number of particles. Okay? So in this formulation, large charge is like a large number of particles. But you can just use that formalism to study 2 particles, 3 particles. It's all equivalent to the Schrodinger equation. You just start from the Galilean. Well, you start from the Schrodinger vacuum. This describes 1 particle states. This describes 2 particle states, etc., etc. So you can study sectors with any number of particles by just acting with psi dagger on the vacuum. Psi dagger is a creation operator in this formalism, because psi dagger is conjugate to psi. Okay, so this is just a formulation of undergraduate quantum mechanics that's a little bit more convenient. And now to what is the connection between the short range potential and that? So first of all, let me just give you the formula for G. And just to get the 4 pi's, there are some nasty 4 pi's in there. So G is 4 pi h bar times A, h bar squared divided by the mass. So if A, what was A? A is this coefficient here. So if you look at delta 0, that's the phase shift in the S wave. That's Ka. There is actually a minus sign here. Delta 0 is minus Ka, and that's how A is defined. You look at the phase shift in scattering in head-on collisions. You take the low momentum limit. That's how A is defined. And it's the same A that's going to appear here in the quartic interaction. And so neglecting additional quartic operators with derivatives corresponds to our assumption that there is only S wave scattering. If you want to study quantum mechanics with P wave scattering, you need to include additional operators with 2 derivatives, like that. Okay, that would correspond to L wave scattering because of the 2 derivatives. P wave scattering, and so on. So the fact that I'm only including a non-derivative quartic interaction is like saying that we've used the Fermi pseudopotential, or it's like saying that we're using universality, and this is going to be irrelevant. So we are used in field theory to the idea that this kind of operators could be relevant in some appropriate circumstances. So that's the same idea here. And that's why I'm keeping only this term.
That's how people came up with this potential. They wrote down something like an action like this, and they tried.
So I think Fermi came up with the pseudopotential by looking at a sequence of potentials, which are like shells where the interaction happens. It's a sequence of potentials that makes all the phase shifts go to 0 mathematically in some double scaling limit. It's called a pseudo-potential because what you get is not a delta function. Maybe I should say it for just maybe some of you are curious. You could ask, why is the right answer not a delta function potential? Repulsive function. So the answer is that this doesn't make sense. You have to regularize it a little bit. Find out that this doesn't, there is no such regular in 3 + 1 dimensions. Because the kinetic energy goes like nabla squared, that's like 1/r². This goes like 1/r³ in some sense. It's just a little bit regular. You cannot solve the Schrodinger equation unambiguously with this potential. Okay? So that's not the answer for the short range interaction. And that's why Fermi did something a little different. So the actual answer turns out to be that. So you need to put a derivative in the operator in the Schrodinger equation. I don't want to go into the pseudo-potential now. But I'm just saying it's not a delta function. It's a slightly complicated exercise to find the potential. Now, the thing is that it doesn't really matter what the potential is because all these other operators are going to be relevant anyway. Okay? It's just a mathematical curiosity. How do you exactly reproduce that thing from a short-range potential? Yeah.
Why we think of psi dagger as a creation operator, and we don't have to expand it in some basis of creation and annihilation operator.
That's actually going to be a super important. So the question is, why is psi dagger a creation operator? That's going to be a very important thing for later on. So this is just this looks like field theory, but it's just the Schrodinger problem. Because if you fix the number of particles, it reduces to the Schrodinger equation. But why? So what is the conjugate momentum to psi? It's psi dagger. And therefore, psi dagger psi is that up to some coefficients, right? So this is, let's say, r, and this is 0. So that's one thing. Another thing is that the charge, the U1 charge, which is particle number symmetry, is that. This integral is the U1 charge. So therefore, psi dagger psi is particle number. What does it mean? It means that if you had some state, let's say some state, and you acted on that state with psi dagger, what would happen to the particle number? Particle number is the normal ordered product of psi dagger psi. So particle number is that. So if you act with psi dagger psi on that, and you use the commutation relation, and you integrate over space to check what's the total particle number, you'll see that the particle number increased by 1. So in a non-relativistic system, we can just say that the number of particles is exactly given by the U1 charge. In relativistic systems, if I tell you that the charge is 7, it doesn't mean that there are 7 particles. There could be 20 particles and 13 antiparticles. But in this system, because the time derivative is first order, the action has a first order time derivative, the number of particles is what it is. There is no fluctuations due to antiparticles. So you can just say, I want to study all the states which have 7 insertions of psi dagger and diagonalize the Hamiltonian on those. There are no terms in the Hamiltonian that would mix it with any number of mix it with states with another different number of psi daggers acting on the vacuum, right? So that's why this formalism is the same as the Schrodinger equation. Yes?
My understanding of that question, or at least the question that I now have, is why don't we expand psi in creation annihilation operators with like e to the I kx?
Oh, you can. Yeah, psi dagger x can be expanded in any basis of one particle states that you like. It's a function of x and t. So it can be expanded in any basis that you like. I'm not saying that acting with psi dagger xt on the vacuum is an eigenstate. I'm just saying it's some state which has one particle. But you still need to diagonalize it. And you are going to find the same one particle wave functions that you know from quantum mechanics. Okay? Any other questions? Okay.
So maybe I missed it,
for this action are non-linear, but the Schrodinger equation is linear, so what?
Fantastic question. So, so the question is, how come the Schrodinger equation is linear and this equation is non-linear? Okay? So there is a dictionary to go between this formulation. You agree that both are difficult. It's not like one is a trivial problem and one is, okay. So there is a dictionary. If you take, you can write the Hamiltonian from the action by the usual way of going from the Lagrangian to the Hamiltonian. You can say that this is the integral over the Lagrangian. You go to the Hamiltonian, and then you try to diagonalize the Hamiltonian on states of this form. These are one particle at x, one particle at y. You will get the differential operator that you're familiar with from undergraduate quantum mechanics, acting on a function of two variables, which is the wave function of two particles. Okay? And the quartic interaction, what it's going to do, it's going to reproduce for you exactly that piece of the story. So the full differential operator that acts on a function of two variables in the two-particle case has this term. And if you act with this operator on such states, you will get a linear. So I'm just saying, even though it looks non-linear, when you act with the Hamiltonian, there is a Hamiltonian corresponding to that. And this Hamiltonian acts on some wave functions in second quantization, which are products of psi-daggers. So this is a linear equation. So in second quantization, we also have a linear equation. Quantum mechanics is always a linear equation. It's just that a nonlinear Hamiltonian in this formulation gives a many-body problem with interactions in that formulation. But both are fundamentally linear, because quantum mechanics is always linear. Okay? Yeah.
Can you just go back to that short-range potential and clarify what is a universal property when we're only interested in short-range interactions, and what are assumptions? Because you use the word universality and assumptions.
So you might, let's say, choose when you have two atoms and you think this problem is like atoms in some trap, and when they actually interact, there could be some very complicated potential. We expect that maybe the actual macroscopic physics, the properties of these atoms in this trap may not depend very much on how they interact, right? You might expect that it may not be very important. So what we expect is that the only thing that matters is what happens when atoms collide with each other head on, okay? And that's captured by delta zero. So what we're doing is we're assuming that the short range potential is whatever it is, but we're going to assume that everything vanishes other than delta zero. And that's what that formalism captures.
Is this shown by experiments? Or?
It's shown by self-consistency of the solution. So we will find the solution, and then we can ask what happened if we were to reintroduce back some delta 1. That corresponds to adding another term here with derivatives. And you could then see retrospectively that it's completely negligible. So it's done by self-consistency. You can't be sure that it's going to be correct, but that's the statement of universality. That just happens to be correct. Okay? Okay, so let's move on. So I'll just give you some examples. I don't remember if that's the precise experiment. Oh, no, that's the MIT one. I'll give you numbers that correspond to what people did in the MIT experiment of Ketterle. Unfortunately, I wasn't smart enough to borrow numbers from the Colorado experiment. So an example, it's just an example, so you have some numbers in mind. So the MIT experiment was about sodium-23, so 12 neutrons, 11 protons. The scattering length, A, I forgot to say that this A is called the scattering length, was, of course, atomic scale, -9 meters. The density was 10 to the 20 particles per meter cubed. the size of the sample, this is the trap, was between 10 to the 4 and 10 to the minus 4 and 10 to the minus 5 meters. And the number of particles, which you can calculate from multiplying the density by the volume of the trap, well, it ranged between 10 to the 6 and 7 particles in the trap. So these are the characteristic numbers. Okay? That's just something that you can keep something in mind. So now I'll show you how to solve this problem. So now you'll see the magic of large quantum numbers for the first time. I'm going to be able to do some simple change of variables. And just out of the blue, find the ground state when the number of particles is very large. And the ground state would look very different from what you might expect. So what might you expect if you didn't know anything? If you didn't know anything, you would say, well, if there is no short-range interaction between the particles, they'll just sit in the ground state of this harmonic potential or the ground state of the bucket. And then the short-range interaction happens only when they collide. That's very infrequent, right? So who cares? It's going to be a small perturbation around the wave function where the particles are just in the ground state, and that's it. I think it's a fair expectation of, because it's very dilute. You can see that it's very dilute in this example. It's just like 100,000 particles, maybe 1 million particles. It's very dilute, so who cares about the short-range interaction? But this turns out to be completely false. And it's false for the same reason that, well, it's false because perturbation theory in the short-range interaction cannot be done. Like our intuition is perturbative. We always learn to expand around the harmonic oscillator. And that's the only thing we know how to do. But it completely fails in this example. You'll see that the macroscopic properties of this object are very different from just single particle states which kind of infrequently interact with each other. Yes?
Sorry, don't we want a boson? How do we get a boson out of something that has 23 nuclei?
Oh, we didn't strip it out from the electrons. It's not just the nucleus, it's the whole atom. So there is the spin of the nucleus is 3/2, and the spin of the valence electron is 1/2, and it's a spin 2 atom. Okay? Any other question? That was, you almost caught me off guard. But I actually thought about it myself a few months ago. I was confused. Yeah, it's a very interesting thing to think about philosophically. Why does perturbation theory not work? It does work in some regime. So you'll see the parameters that appear, but there are some regimes, maybe I should say that because I'm not going to have time to go into too many details, but you can make an important length scale out of these parameters. I'll just say what regime perturbation theory breaks down. So let me just say that. There is an important length scale that you can make out of this mess, which is the density times the scattering length. That gives you a length scale to the power -2. That length scale is called the healing length. So I'll just write it. That's called the healing length. Now, if I calculate it in this example, I think you get like 10 to the -6 meters for sodium. And this length scale is what captures perturbation theory, your perturbative intuition versus the true answer. So the regime of all these experiments in Cornell and Boulder was that Xi is much, much bigger than the actual scattering length. So it's a macroscopic length scale in that sense. And it's much smaller than the size of the trap. You see there is a factor of 10 here, maybe 100, and a factor of 100 or so here. In this regime, perturbation theory breaks down completely. If Xi was much bigger than the size of the trap, perturbation theory would work, no problem. Okay? But this is the regime where these experiments developed a completely new phase that you cannot understand intuitively. Okay? So that's the. In the notes in Slack, you'll see the full derivation of why this is the dimensionless parameter, why does perturbation theory fail. I'm just giving you a taste here. So how do we do the large n limit? And so that's the main thing I wanted to show you. So there is a so look at this action. Where does n appear? It appears here. So it's hard to understand what's the large n limit in this formulation. But let's do something very dumb. Let's just rescale the wave function by n. What this arrow means is that everywhere that there was psi on that board, I'm going to write square root n psi. I'm not going to introduce new notation. That will be just horrendous. Okay? So now we get a new action where there is n out front of the integral, and that's a great sign. That's what we want. So let me just write the new action, and you can just check in your head that what I'm doing is correct. So I have I h bar psi dagger psi dot minus psi dagger h bar squared over 2m nabla squared psi minus psi dagger the trap psi. And finally the quartic interaction, but now the quartic interaction has a new parameter g prime. I will need to rescale g prime. I'll explain what g prime is in a second. You might say that I just got rid of n in the number of particles equation, so now this is normalized to 1. So what's the advantage? Why did I do that? Two things. One, now n is in front. That looks like our effective h bar. Another thing is that now the wave function is normalized very nicely. I don't have a factor of n here. But the price is that I have a g prime. And I have to understand what to do with this g prime. So let's write the formula for g prime. G prime is g. G prime is 4 pi h bar. Let me just put an h bar here. This is 1 over h bar times the action. Okay, sorry. That will be better. So g prime is 4 pi h bar na over m. And you might say, oh, n is here now. What's the point of this whole exercise? I still don't know how to take the large n limit. But the point is that this will be kept finite. So we will just assume that this is finite. And that's the appropriate limit in this called atom experiments. We imagine that the number of particles is huge, and this is kept finite. What does it mean to keep it finite? I don't literally mean that this can be kept finite, because this cannot be kept finite. What can be kept finite is this. So what really is kept finite is g prime over the volume of the sample, because then you get n over the volume, that's the density. Then you multiply the density by a, that's the healing length. So we're imagining a sequence of theories, right? So that we can rigorously do an expansion where n keeps growing, but the healing length stays finite. It's a sequence of theories. How do we achieve something like that? When n keeps growing, the density increases, but we just make the sample bigger so that this stays constant. Okay? So we're imagining a sequence of theories where g prime is finite in this sense, of g prime over the volume being finite, and then we can take the large n limit. So it's like a double scaling limit of a sort. Is that clear? So that's the main idea. So the main idea is that in this regime, that's why Xi is finite essentially. That's why this limit is interesting exactly here, because we keep the healing length finite and much bigger than the scattering length, but much smaller than the sample. And in this limit, taking large n in this way makes perfect sense. If you are in a different regime of this interacting boson gas, where Xi is not kept finite, you have to do something else. You have to invent a new method, or maybe resort to numerics. That's what's called the dilute gas limit with a finite healing length. Is that clear? That's maybe the most crucial point, that now we can take the large N limit, and it makes sense when G prime is kept finite in the appropriate sense. So just think about G prime as finite. Yeah?
You took an H bar out of the old G to bring it up to the
Yeah.
reaction. Don't you have H bars in the size then?
No, I think actually what I wrote, okay, I made a typo, you're right. There is a typo here. Yeah, you're right. There are two typos. And yeah, three typos, I'm sorry. Yeah, I'm sorry. So, but my point was, what's the effective H bar in the system? 1 over n. So we can now treat this field theory as a classical field theory, because we've been able to achieve weak coupling effectively in this particular limit. So now I'll show you what can, and a huge amount of work can be done, because now we have a classical field theory with a nonlinear differential equation. Where did that come from? That wasn't there in the first quantized formulation, but it just appeared. And of course now, mathematical physicists are happy. They have a nonlinear differential equation to try to prove theorems about. We know that this is just an approximation, but there is a whole community of mathematicians that for them this equation is sacred. And they just analyze this nonlinear differential equation. So what is the nonlinear differential equation? We just take a variational principle, because when h bar is small, what are we supposed to do according to the Feynman path integral? We just look for saddle points, and then we expand around the saddle points. That's called semi-classical physics. So we have a nonlinear differential equation, psi dot. I'm going to write it with typos. So this is just without coefficients. It's not in my notebook, so there is no way I'll get it straight. But I'm just going to write it with h bar equals m equals 1. And, you can just do the variational principle later. So there is going to be that. And then there is going to be that. This is still a linear differential equation. And then finally, there is going to be G prime psi dagger psi squared. That's a cool nonlinear differential equation, has time evolution. There is endless literature on solutions. And the classical saddle points correspond to some interesting configurations of this gas. And you can use that to predict the energy levels of the gas. I'll do one example in the remaining 15 minutes. Are there any? Sorry, this equation is called the time dependent, because there is a time derivative. Gross-Pitaevsky equation. So this is a big equation in mathematical physics, and people proved the existence and uniqueness and various kind of things about solutions. There are many interesting solutions. There are vortices, lattices of vortices. For us, this just arose as a saddle point equation. Yeah.
So you said that we want to have the NA effects, the little n times a effects, right? But that in that case, that means we have to increase the system size, which is the L. But I think isn't the V trap is something like has a length scale as L as well, because you trap it into a system with size L.
Yes.
So if you change L, it's like you are also changing V trap as well.
Right. So, sorry, the question is really about the order of limits. And just to repeat the question is about the order of limits in which this analysis makes sense. this whole large n limit. So if you assume that, then you're in a regime where this analysis makes sense. Because in this regime, Xi, which is the, so, yeah.
Say it this way. I think V trap is also changing, right?
Yes, yes.
So is that we change both V trap and G pi? No, we fix G pi, but we change V trap in this case, is it?
Yes. Well, you can sorry. So you take a limit in such a way that Xi is fixed, and you can imagine that you take n ever increasing. So there are several ways to take the limit. If you want the most conceptually clean way, so that the action inside the brackets does not change, it's the following. You increase n, the number of particles. You decrease the scattering length a, so that Xi and L are held fixed. Because little a does not appear in the action explicitly, only the healing length appears in the action explicitly. That's a very clean limit in which whatever is in the parentheses does not change as you take the large n limit, and only the prefactor change. So it's like you have a fixed system and you just take h bar to 0 continuously. So it's a sequence of theories with ever decreasing correlation, with ever decreasing scattering length. That's one way to make it very clean. Of course, in practice, we have a finite number of atoms in the periodic table. So how do we take A to be arbitrarily small? You know, yeah. So in practice, when you have a fixed system, you don't have a sequence of theories. So you just apply the results of this method if you're in this range. Then it makes sense. Yeah.
Maybe my question after that one now is, or maybe this is what he was asking. Does V trap depend on L? And if so, it seems like it'll also depend on N as we take this double scaling limit.
So the question is again about the order of limits. There is a cleaner way to do it, in which you don't need to change the trap potential.
Okay, perfect.
And the limit is the following. You imagine that there is a sequence of atoms for which this is kept fixed. So A decreases, N increases, and L is kept fixed.
Okay.
You just imagine that there is a way to do that somehow with atoms.
Okay, perfect. Thanks.
Yeah, and then it's very clean mathematically. It's a very clean double scaling limit. Yeah.
Sorry, I think I missed this detail, but when you rescale and put the action in this new way, is n still the number operator?
It's the number of particles.
Yeah, but it's in the second quantization, right? Shouldn't it be like the number operator that you can act on a state with?
It's the, yes. It's when we write that in second quantization, I should put expectation values here. So what I'm doing is that I'm assuming that I have some fixed number of particles, and then I'm rescaling the wave function in that way. Yeah. Okay, let's just do the simplest example in the remaining 15 minutes. What's the simplest example is just a bucket. The harmonic potential is just a little bit, it's just a little nasty to solve this equation in the harmonic potential, but it's in the notes. I'll do a bucket. So the particles are dropped into a bucket. Bucket means that the potential is infinite here and 0 here. It's the simplest trap you can imagine. And you need to solve the Gross-Pitayevsky equation in this background. So we have this, and we have this nonlinear term. And also we have a constraint. I forgot to write it. There is a constraint. Okay? I forgot to write that there is a constraint in the conventions that we've chosen. So what's the solution? Can anybody suggest a solution? There is an immediate solution that's in the bucket to the nonlinear equation. What should I write? Well, Well, a constant wouldn't solve this equation because you see the nonlinear term would be activated, but the left-hand side would not be activated. So you just need something that oscillates in time. So you put the square root of the volume of the bucket, and then time oscillations. And it's very important to get the sign straight. I'm afraid I have not got it. I'm afraid this is the wrong sign. In the notes, it's correct. Okay. Hopefully, that's the right sign. And mu is just G prime. Mu is G prime over the volume. And guess what? You've already seen this quantity. That's proportional to the healing length and to the power -2. So in this limit, the chemical potential is fixed in this double scaling limit. So that's a very nice solution. And you can use this solution to calculate some interesting macroscopic properties of this. It's actually very confusing because what the hell does it even mean? I told you that psi dagger is the raising operator and psi is the lowering operator. What does that even mean? It's a classical solution. So there are other saddle points. I can put a different phase here. So this should be interpreted as the spontaneous breaking of U1, particle number. So the proper way to think about it is perhaps that the expectation value of psi is non-zero. That looks very confusing from the way we've arrived at this whole formalism. Yeah.
How can this satisfy the boundary condition? I think it should be 0.
Yeah, and it's 0 outside, of course. Yeah. Okay, excellent question. So the gentleman here says that we have some constant solution here for the wave function, and then 0 here. And the gentleman very smartly worries about what happens at the boundary, because it seems that the derivatives are discontinuous or something bad is happening. The wave function is not approaching 0. So this is an excellent question. Near the boundary, you cannot neglect this term. You cannot neglect this term. And it turns out that what happens is that if you take a small region here of the size of the healing length, you need to stitch the solution to a new solution that mostly goes to 0. And the reason it's called the healing length in the atomic and the AMO literature is because it's the size, typical size in space from which the wave function takes to go from 0 to non-zero constant value. So it's basically constant everywhere, except in a small window, which is called the healing window. And then it mostly goes to 0. Okay, so to actually find the solution, you need to stitch it here. You can do this exercise. It's very nice. Any other? Okay, so the interpretation of this formula is very confusing because we said that psi dagger is the number of particles. What does that mean? This should be interpreted as spontaneous symmetry breaking. Particle number is spontaneously broken, and we lost. And when we expand in fluctuations around this solution, there will be what we previously called particle number in quantum mechanics will not be diagonalized. Would not be diagonal. We'll do that exercise either today or maybe early tomorrow. So we have so this solution breaks particle number spontaneously. It's also called the superfluid. You can calculate the properties of this solution just from thermodynamics. So for instance, the speed of sound, let me just write some formulas here that you can check. The pressure is the derivative of the energy with respect to the volume. That comes out to be G times n squared with a half. And the speed of sound is the derivative of the pressure with respect to the density. And that comes out to be the healing length to the power -2. So it's a new phase of matter, you could say, very different from bosons in a trap, which has sound. So if you hit this fluid here, the bosons basically become a fluid. That's what you should imagine in your head. It becomes like, so if you hit it here, there is a wave that's propagating with that speed of sound. Okay? So we got a completely different phase out of this problem of non-interacting particles with very small short-range interactions, where it behaves collectively like a fluid. And it has speed of sound, it has pressure. None of these things existed before, if it was a perturbatively small interaction. Any questions? Now, in the last 5 minutes, I'm going to do the mode expansion around this solution. This is, again, a classical field theory exercise. We have a nonlinear Gross-Pitevsky equation. I'm going to diagonalize the small fluctuations, and we will see that, indeed, we have sound modes. Yes?
Are there other possible solutions to this equation with this potential?
Yeah, there are many other solutions. There is a whole bunch of mathematicians that classifies. Of course, this is the ground state, and this is just fluid at rest. But you can ask, what happens if somebody rotates the fluid? What happens if somebody kicks the fluid? There are solitons, there are vortices. There are many interesting solutions.
How do we know that this dominates the path integral? Like, could there be some nonlinearity that makes it shrink down to 0 or something?
So the question is, how do we know that this is the ground state? We have to ask mathematicians, to be honest. Yeah, but yeah, there is a mathematician in France. Do you remember her name? No. People proved theorems that the lowest solution with no angular momentum is this, and then, yeah, there are rigorous theorems about it.
Like one thing to see.
Aftalion is the name. Yeah, her name is Aftalion.
Newtonian would have a term which is like the nabla square, and a constant in space solution is like it will have anything that will have space dependence will have some penalty from the Hamiltonian.
There is some penalty that you have to pay here because of the remark of this gentleman, because you have to stitch it. There is a little bit of penalty near the boundary, but it's a boundary effect. It's clear that it's a minimum because there are no space variations, but you have to still prove things, and the existence of a minimum is not something that's taken for granted. Okay, I just want to do the expansion, just the small fluctuations of this fluid, yeah? Because we discussed just a fluid at rest, but there are some waves, and the waves can travel, and we use thermodynamics to calculate the speed of these waves. I just want to show you the spectrum of these waves, how much it deviates from the Schrödinger problem. Because in Schrödinger particles, the dispersion of waves is that the energy goes like momentum squared. That's the Schrödinger particle dispersion. We started from Schrödinger particles, but the waves here will have a completely different dispersion, very different from weak coupling. So I just want to do that in the last 5 minutes, and that's it. In the notes, you'll find at least 20 pages on how vortices behaves, what are rotating solutions, many other things, many other solutions. So I'm just going to do the mode expansion. So a fluid at rest is given by this weird wave function that breaks particle number spontaneously. That's a configuration that breaks particle number, but it's stationary in time. And then we imagine that maybe somebody kicks the fluid and waves start moving. So we parameterize them by some time-dependent amplitude, k, with spatial profile e to the ikx. Okay, and we just shove it into the nonlinear differential equation and find the dispersion of these modes. Is the exercise clear, or somebody wants me to do it? It's laid out in details in the notes. You just shove this ansatz into the differential equation, linearize in mk, and find the time evolution of the amplitudes. And from the time evolution of the amplitudes, you read out the dispersion. Classical physics. So when you do that exercise, you find the following remarkable result. You find that the dispersion of the K mode is given by some formula G prime H bar, then the volume times the mass of the sodium atoms, then K squared plus H bar squared 4 times the mass squared, and then the momentum to the 4. And then there are two interesting limits. Small momentum modes of the fluid and large momentum modes of the fluid. So let's go to small momentum first. For small momentum, this is negligible. We just pick out something from here, and we get 4 pi h bar divided by the mass times the healing length times the momentum in absolute value. This is the dispersion of small momentum disturbances of this fluid, and it's linear in momentum. It's not a Schrödinger particle anymore. The particles have transmuted to relativistic particles. This is the dispersion of a relativistic particle, but with the speed of sound instead of the speed of light. And the speed of sound is given by the healing length. That's what we keep fixed in our double scaling limit. In the opposite limit of very high momentum waves, we actually get just Schrödinger particles because this dominates. And of course, well, it's just h bar over 2m. So we just get what we expect from Schrödinger particles. Okay? So they don't see the fluid, these guys, but these guys behave like sound waves or relativistic waves. So we see that we got a completely different phase of matter with linear dispersion, and we kind of solved the quantum problem in the many-body limit that we get a fluid with relativistic dispersion. And that allows us to compute the spectrum of energy eigenstates. We just have these phonons. These are called phonons, or sound waves. So that's an example of how we basically solved the large particle number limit without any work whatsoever in a simple trap. Are there any questions about it? I'm done for today, introducing the idea of large quantum numbers. Yes.
At the very end here, you analyzed the long wavelength limit, and like my RG intuition would tell me if I want to analyze that in the action, I have to care about the relevance or irrelevance of the terms.
Yes.
It seems to me like the psi 4 term is irrelevant, so I'm confused about how it can be affecting so.
So the question here is how come we got something so distinct from Schrödinger particles, even though this looks irrelevant? So what's the answer? The answer is that yes, it's irrelevant in the sense it's irrelevant in the RG sense. So if it it's given by a length scale. So you would say if I go to long distances, the effects of this term should die out. But first of all, note that when we solved the nonlinear Gross-Pitevsky equation, this was the only important term. So the whole physics came just from that term, because we wrote this solution, and this was that. So if for some reason there was no quartic, this whole thing makes no sense. There is spontaneous breaking of particle symmetry in a superfluid only because G is non-zero. Okay, so what's happening here? What's happening